Hey physicists, we'll take a look at a few more ideas involving Newton's third law. Again, Newton's third law is for every action there's an equal and opposite reaction. We'll come back and visit our video with the head and ball collision. Okay. Hey, so what Newton calls an action, we call a force. And what Newton calls a reaction, we also call a force. In this case, ball hits head, head hits ball. That's referred to as a pair of forces. So forces always come in pairs. Okay. The ball can't hit my head without my head also hitting the ball. Let's analyze this a little bit more. Okay, so the head was certainly experiencing an unbalanced force. It went from rest to moving to the right, so I know there was an unbalanced force. How would I label that? I'd have, using my force type feeler dealer label, I have a force type normal, feeler head, dealer ball. So force, normal, head, ball. Hey, what's the pair to that force? For every action, there's an equal and opposite reaction. Okay, it's the head striking the ball. We see that here. The force, the type, normal on the ball from the head. Make sure that these two do not end up on the same force diagram. These are talking about two different objects. This is the force on the ball. This is the force on the head. But how are they related? They're the equal and opposite reaction. Okay. Hey, let's take a look at Newton pushing off against the elephant. In the previous case, both the head and the ball had about the same mass. Here, Newton the elephant do not have the same mass. Okay. So as Newton pushes on the elephant, we have a force normal on the elephant from Newton. Let's take a look at what that force pair to that would be, acting on the different object, Newton. We have a force normal on Newton from the elephant. Hey, but what's that going to do for motion? We do know that net forces are equal to mass times acceleration in both those cases. But let's see what it does for the elephant. Okay, we have that force acting on a very large mass, so the acceleration must be less. But on Newton, that same force is acting on a smaller mass, so it must have a large acceleration. Newton accelerates more as a result of his interaction with the elephant. Let's go to a more extreme example and something that in normal life we wouldn't expect. And this is the idea of the interaction or collision between a bug and the windshield of a car. We normally look and say, hey, the car must hit that bug a whole lot harder than the bug hits the car because one splats and the other just continues on. Okay. So really, it's like, why does this happen? Why does the bug splat if the bug hits the car just as hard as the car hits the bug? Well, while the forces are the same, the acceleration is much different. Just like with Newton the elephant, we saw there was a difference in acceleration. The acceleration between the bug and the car will be as different as their masses. Let's go ahead and do the calculation on that. So if we are given a car with a mass of about 500 kilograms, that's a pretty light car, and a bug mass of about 20 milligrams, that's actually pretty heavy for a bug. And milligrams we can convert to 0.00002 kilograms. And we're just going to make an estimate of the impact force between the bug and the car, which would also be the impact force between the car and the bug, of 0.04 newtons. Let's take a look at the acceleration of each of those. And of course, acceleration is our net force divided by mass. So for the bug, we take a look at that force, 0.04 newtons divided by our mass of the bug, 0.0002 kilograms, and we end up with a value of 2,000 meters per second per second. That's, you can see here, a lot of change of motion, or a very quick change in its velocity. This is over 200 times as much acceleration as we would get due to gravity. But how about for the car? Let's take a look at that. For the car, that same force, 0.04 newtons, we divide that by mass to find out the acceleration. So we're dividing by 500 kilograms. We end up with a value of 0.00008 meters per second. Something that wouldn't even be noticeable. A very, very slight change in mass. Okay. So why does the bug go splat? Because it has such a huge acceleration. Why does the car continue on? Because it has such a small change in its motion, or a small acceleration. Okay. Hey, so motto of that, or just a conclusion, that's why big cars tend to be safer in an accident than a small car, or particularly why a car is safer than being on a motorcycle in an accident. Larger mass means a smaller change in motion. Hey, so let's take a look at another practical situation. How can Stephen Curry jump? Okay. We know that an object cannot apply a force to itself, but we can only apply forces to the objects and things around us. So how does Stephen Curry jump? Okay, well, first he pushes down on the floor. Okay, what's the paired force to that? If he pushes down on the floor must push up on him. If the force up is more than his weight, then it'll end up traveling into the air. Continue up until gravity slows him down. Once he leaves the ground, then hey, its gravity is going to end up taking over. What he has control over is how much force he can exert against the floor. By exerting a lot of force against the floor, that means the floor will exert a lot of force against him. If it's more than his weight, he'll come off the ground. Now, how about the condition where we don't have something to push against? And an example here is, hey, what if we have a spaceship that's outside the atmosphere? There's nothing to push against. Okay, how can that end up continuing to move or accelerate? Well, the first thing is, if we actually take a look at the spaceship and all its fuel, no, it can't. If we were to draw an enclosure that went around the spaceship and its fuel, the only interaction would be with the Earth and gravity. But that's not the case. What we're really only interested in is looking at the rocket ship, and we kind of throw the fuel away. Okay, so how do we end up doing that? Okay. Hey, so the rocket ship pushes the fuel down. We can see that here. We know there's a lot of acceleration. Our fuel starts at, let's say close to a zero velocity, and achieves a very high velocity as it exits out of the back of the rocket ship. Okay, there must be a lot of force that the rocket ship is applying against the fuel. Okay, so if the rocket ship is pushing down on the fuel, that must mean that the fuel pushes the rocket ship up. That's how we get into outer space. That's how we end up moving around even when we don't have something to push against. We push against part of ourself, but then we're only worried about the rocket ship. What does that tell us? It tells us the importance of, when we end up making our enclosure, that we only include the object that we're interested in. Okay. That we then end up having, hey, say gravity down, but we also have the rocket fuel pushing against the rocket ship pushing against the fuel. If I were to make a interaction diagram for the fuel, I would have, in addition to gravity, I would have the rocket ship pushing against the fuel. Hey, so now some just last couple notes on Newton's third law, or for every action there's an equal and opposite reaction. First is, okay, that forces always come in pairs acting between two objects, the feeler and the dealer. And which is the feeler and which is the dealer is just the object that we're going to analyze. We always analyze the feeler. All the things that are acting on it are the dealers. Okay. What about these force pairs? Three things to keep in mind. One is that the pair of forces are always the same type. I push against wall, wall pushes against me. If I'm exerting a normal force against the wall is exerting a normal force against me. Two, they're the same magnitude. I push against the wall with, say, 10 newtons of force. The wall is pushing back on me with 10 newtons of force. And the last thing is they're always in the opposite direction. Say on that same wall, I'm pushing to the left on the wall pushes back to the right on me. Okay. The last points. Hey, get those points down and you'll know the mind of Newton. Good luck.